Good afternoon, everyone. Welcome to today's CITRIS Research Exchange. My name is Ken Goldberg. I'm a professor in engineering, College of Information, school in the Department of Art Practice, and I'm pleased to be also the director of the CITRIS People and Robots Initiative, which is co-hosting today's lecture. We are delighted you're here. I want to ask you to silence your cell phones, and also please consider holding questions until the end. We're also televising this, not televising, we're webcasting this to other campuses, and we're also recording it. So that way we'll pass around microphones to collect those questions. Over the past 10 years, CITRIS has hosted a remarkable lineup of technologists and leaders on this stage, and we're delighted to continue this tradition. Tomorrow, in fact, we have another speaker, February 6th, at same time, on our View from the Top series. We'll have we'll have Tara Bunch, who's a Berkeley alum and Vice President of Operations at AppleCare, talking about the road less traveled. And then on February 12th, next week in the same series, at Wednesday at noon, we're going to have the Vice President of Ericsson Silicon Valley, who will be talking about the intersection of 5G, edge computing, AI, machine learning, and the Internet of Things. So please join us for that as well. The CITRIS People and Robots Initiative, as many of you know, involves all the campuses, as over 50 faculty and several hundred students engaged in research on robotics, and in terms of theory, benchmarks, software, and methods that address this intersection of humans working together with robots. And I think this resonates very, very much with the research interests of our speaker. He comes from Google, which has really been a pioneering force in the field of robotics. As you know, Google was a very early champion of self-driving cars. It has also made major investments in a number of robotics companies, has released a huge volume of code, open source data sets, and I think that we all appreciate the publications that Google has so generously shared by opening their research to the world community. Our speaker today exemplifies this, and is actually, I was thinking, his history comes from France. He did his undergraduate at École Centrale in Paris before he came to the U.S. And I was just thinking how many of the great deep learning researchers have come from Europe. And we tend to think of it as somewhat originating in the U.S., but actually so much of the top researchers are international. And Vincent has come to California. He has led a phenomenal team, and he is building up the robotics program to the point where he is now the head of robotics at all of Google. He's also the co-founder of the conference on robot learning that was established 3 years ago and is now is going to be at MIT in the fall. He has done work in many aspects of machine learning prior to the increase of attention on deep learning. He has work in speech recognition, computer vision, and robotics. And he also has generously shared his insights. He has a lecture series on Udacity. It's been seen by some 100,000 students. And he also has a blog on Medium that I encourage you to check out. It's fantastic. There's an article that I really like, So You Want to Be a Research Scientist, that he published last year. And I would say there's some great points up here about, it's all about ill-posed questions without clear answers. You'll spend your entire career working on things that don't work, and so on. So there's a number of great insights. And he's a great mind. I've had the pleasure to be his friend for many years now, and he's always interesting, always insightful. Please welcome Vincent Vanhoucke.
Thanks for the very kind introduction. So, yeah, my name is Vincent. I've been leading the research effort in robotics at Google for a few years now. The goal of our research team at Google has been to try and make your robots useful in the real world through machine learning. And you might wonder why restrict ourselves to through machine learning, why not make robots useful, period. We're pretty opinionated about this because we are essentially a research team, and the space of things we could be researching on is essentially infinite. And I've always found that adding artificial constraints into the space that you're exploring is actually very productive in the sense that it helps you really go deep in your research and really follow through on your hypotheses without giving up and going for possibly the road more traveled. So my goal today is going to be to try and convince you that this intersection of robotics and machine learning is actually a very, very fruitful space to be in, and that it may have really, really important consequences on the world of robotics and how we envision what robotics might look like in the future. The way this all started is with computer vision. Right, so I assume most of you in this room are familiar with the fact that the world of computer vision has really been revolutionized in the last few years. And I have to be a little careful about saying the last few years because it's almost been a decade when things have started working, and we forget to keep track of that. Things really started moving in 2010, 2012. In a major way, but the rate of progress has really accelerated, and really in the last few years, a lot of things have happened that really make computer vision work in a way that wasn't possible in the past. And I won't go into all the details about how computer vision has really changed. I want to highlight two specific directions, two specific features of this computer vision revolution that really pertain to the problem of robotics. The first one is, for the first time, we have access to both the semantics and the geometry in the world, essentially the what and the where. For the longest time, it was extremely embarrassing. We couldn't tell a cat from a dog with computer vision. And on the other hand, geometric computer vision and understanding where things are and the structure of things in the world was making great strides. And in fact, robotics has developed a lot of tooling around geometric computer vision that has been very effective. So now we have access to the what. And that really changes how we can treat vision and perception and how we can integrate information. So this is an example of a piece of work that from my team, recent, about instance segmentation of objects in images. As you can see, a lot of the objects in the scenes are able to be detected, recognized, segmented at a very precise level, isolated. Different umbrellas here are being treated separately. It's not just one blob. We are able to inject semantics into this. This is just not just a few pixels. We know it's a surfboard because there is context that tells us it's a surfboard. So a lot of the integration of geometry and semantics is really happening in a big way. What's been fascinating from a roboticist standpoint is that this growth in semantics, these improvements in semantics, has actually had a tremendous effect on our ability to reason about geometry. So let me explain what I mean by this. Just picture the image on the left here, right? You look at it, you know as a human being what's happening in this scene. You understand that there is essentially a ground plane. There is a house there that's essentially a big cube. There is a slanted roof. There are, shrubbery here and there. The semantics of that scene tell you the geometry, what things are, and you can infer from the semantics what the correct geometry is and actually draw a depth map for that scene. What's interesting here is that you did not really invoke any sort of stereo vision, LiDAR, or time-of-flight camera, any of the machinery that people have been relying on to do depth sensing and geometry measurement in robotics. This is all extracted from semantics. It's actually even extracted completely unsupervised. Right? That can change things in a dramatic way, in a sense that right now we're relying a lot on very expensive, to be honest, and often cameras that have very pathological sort of failure modes that we may be able to alleviate by just looking at the pixels and treating the world like a person would do. The other piece that's really important about the computer vision revolution is the fact that everything now is data-driven, right? All the computer vision stack is tunable and optimizable just using data. The way a roboticist looks at computer vision, it's a very utilitarian way, right? You don't look at a scene just for the sake of looking at it. You want to estimate the state of the world. You want to understand what are you looking at and infer from that the physical properties of the world. You want to go from, for example, this is a tea kettle, but you want to mostly know what's its orientation, what's its pose, and what its location in the scene. And typically, that's always been kind of a one-shot thing. If your perception is wrong, your state estimation is wrong, and you're doomed. What increasingly is happening is that we have this machine learning-based perception system, which uses deep neural networks or whatnot, which is what we call differentiable. We can actually take derivatives of it. And what it means in practice is that you can actually optimize this based on the data. So you can basically create a feedback loop where if you have the wrong state estimate, if you have the wrong output from your perception stack, and you can recognize that, you can feed that error back and optimize your perceptual system. OK, so that's the big changes that came to computer vision. The differentiability is actually kind of a subtle aspect in the sense that you would think that it's, you put a neural network in your perception stack and that's all there is about it. In fact, there is a lot more depth to that. A lot of the perception systems are very specialized for specific tasks. This is an example here of video recognition. You want to take a video as an input and do action recognition, recognize what's happening in a video. This entire system, it's a complicated system. I'm not going to go into the details of what it's depicted there. But this entire system can be optimized end-to-end and can be differentiated in. In fact, the reason why it's a jumble of connections here is that even the connections between different modules are being learned using data-driven approaches. So even the structure of your machine learning system is being learned, not just the parameters of your system. Another example is in robot localization. That's also a very classic bread and butter problem for roboticists, figuring out where your robot is. There are a lot of very well-honed ways of doing this. SLAM is one. Typically, this is something that is done with approaches that are fixed, that are very inflexible, and that you cannot optimize by adding more data. Well, now we have the ability to actually reason about those very seemingly non-differentiable problems in a differentiable way using neural networks that have latent representations of the world and that enable us to optimize it entirely end-to-end and improve on them just based on experience and data. So that's changing a lot of things in that respect. And so it feels like we're getting towards a very general and adaptive vision where we can treat a wide diversity of objects. We can recognize what they are. We can recognize where they are. That seems like a roboticist's dream come true. But the roboticists are not impressed. The problem with the new computer vision revolution is that what we've gained in flexibility and generality, we can treat any object, we can look at the entire world, we've lost something in the process. It used to be that when we dealt with perception with, for example, known objects, you knew exactly which tea kettle you were talking about, where you were trying to estimate the state of. You could get very high degree of precision in terms of what you could extract information from that system. You could really measure at a millimeter level the pose and the location of objects. You could really understand the world at a very fine-grained. And if you look at the modern computer vision stack, it doesn't feel like you have that at large for the wide majority of objects or elements in a scene that you would be considering. Because you have to be more flexible, and because there is a lot more unknowns about the world, you cannot go and reason at this level of depth about everything. In fact, people don't do that. Right? I don't really necessarily know exactly at the millimeter level how far this is from me. But I can interact with it. So the challenge for robotics is to get over this lack of precision. And I want to say that precision in and of itself can also become a curse. Right? So this is an example of a robot that is very precisely doing the wrong thing. Right? And in a catastrophic way. Right? Here it's a case where the robot thought that the handle there was in a different position than where it is actually, and it went all in. Right? It committed to that fallacy and completely based its entire planning and decision-making on that premise. And when that premise was wrong, it had a catastrophic effect on the robot. So I think precision can be good if you can have it. Relying on it is where the danger is. There is a cure, though. We don't really need, like I said, I don't think I have this millimeter level precision when I interact with the world. But I interact with it. And so if you can actually learn from your interactions as opposed to assuming that your senses are always right all the time with a very high degree of precision, there's a lot you can correct and you can fix. So this is where we're headed with robotics and machine learning. In a sense, the way roboticists think about a robotic system, you have this perception as an input that gives you a state. You have an actuation, a planner, something that decides on what to do. You take an action, and you look back. Right? You see, act, see, act. That's a repeated process. But now we're saying we have a differentiable perception stack. We can optimize it if it makes a mistake. That's great. But what happens when we actually consider that the entire stack can also be made differentiable and can be made optimizable with data? Suddenly, we can take the action that the robot has done and feed that error signal back to the entire chain. And from the mistakes or from the changes in the environment that the robot is causing, we can optimize the entire chain, both the perception aspects and the control aspects, and have a system that's calibrated end-to-end so that if the perception gets it wrong, you can actually learn to compensate. Or if you make mistaken assumptions about the perception, you can actually compensate for that. What's interesting from my perspective as somebody who comes from the world of large-scale machine learning is that this loop where you have a robot that sends perception to, say, a machine learning system that's going to optimize things and that it's going to send actions back, this whole thing starts really looking like a large-scale machine learning system, right? And so flipping things around and treating robotics as a large-scale machine learning problem opens up the idea that we can now use all the tools that we have and all the tricks that we know as machine learning scientists to address the problems of robotics. So at Google, we love that setting. We've basically thrown large-scale machine learning at everything under the sun. And with good success, we've built a platform with TensorFlow that enables us to be very scalable in that manner. We've invested a lot in a lot of compute to support that kind of those kinds of workloads. So we like that problem formulation. So let's see what it can look like. This is an experiment that we ran a couple of years ago where we put a bunch of robots in a room, all connected to a shared machine learning system, put a bunch of objects in the bins in front of the robots, and basically let the robots loose and to try and do things with the objects. We didn't tell them much. We told them that when by chance they happened to grasp an object, they would get a reward. Right? We would get a positive reward signal only when the objects were picked up. And from that very weak, very simple signal, and from optimizing the entire stack of actuation and perception, we were able to learn what you see on the right here, a robot who can actually pick up any objects in a bin with a very high degree of efficiency. In fact, it's almost perfect. It only missed sometimes the things in the corner because it has a hard time sort of getting to the edges there. But the entire system, what's interesting about this is that those objects that are in the bins there were never seen during training. So the robot is actually generalizing entirely from its past experience to new experiences. We never told it what the objects were. We didn't tell it whether they were soft, they were hard, they were elongated, they were round. The whole system is very agnostic to all those details because it can learn over time directly from whatever the task is. And so the system, I won't go into details about what it looks like, but just as an illustration to tell you that how it's an end-to-end system, we have the image that comes in, we have the state and the actions of the system that comes in, and then we measure what is called a Q function, which is a value function that says, given that image, is taking that action a good idea or not? Right? And that function represents basically the value of taking that action given the inputs. It's a very similar setting to the deep reinforcement learning setting that you may have seen in AlphaGo and in a bunch of other deep reinforcement learning success in the video game space. We're applying this essentially to the problem of robotics. From a system standpoint, it is a distributed large-scale machine learning system. You have robots down here, but they connect, and I'm not going to go into any details here, to buffers that store data and actions. There's a trainer that trains models and loops back and relabels data. I just want to illustrate that this, the robots become a small part of a bigger ecosystem of systems that have to interact together and feed data to each other and depend on each other. What's really fun is that when you start doing things like this, surprising things happen, right? So, for example, we never told the robot how to grasp things, so it has to come up with strategies that help it succeed, right? So it will actually manipulate the objects so that it puts the objects in the right positions so that it's easier for it to grasp. It will do randomization of the objects and pushing them so that it gets to the goal faster. It can correct itself. We did not hardcode any of those behaviors either. If the system misses the object, it will try again and try again for as long as it needs to succeed. And in fact, even if we're adversarial with it and we prevent it from doing its job, it will very patiently, very kindly still try to succeed at its job. So all those things, if you are treating the control aspect differently from the computer vision aspects, you may not be able to elicit those kinds of joint behaviors that depend on, the object is not quite in the place I thought it was, the world has changed, let me correct my actions as a result. Another fun thing is that we relied only on cameras to do this. And so a lot of systems that try to do picking and grasping rely on depth sensing and trying to understand the shape of things. We did none of that. And so it's very robust to even things that are completely transparent because it can see them and it doesn't have to use any form of depth sensing. So it's very general. It has fewer failure modes than if you hard-coded more of the information into the system. And then we get back our precision, right? So just lest you believe that the system is just good at grasping things, here is a task, for example, that is about kitting. It's about inserting little objects in blister packs. And the blister packs are randomized, the objects are randomized, and so the robot has to plan a strategy where it actually goes and very precisely inserts the objects in the blister packs. And it can do that very, very, very high degree of accuracy. The system that's there is, again, a slightly different system, but essentially the same kind of architecture where you have networks that jointly reason about the geometry of things and the actuation and the planning and can be optimized completely end-to-end. Even more fun, when it's no longer just about objects and their shape and their color and their information, what if your problem actually involves their physics? right? This is a robot where we basically taught it to throw the objects into any given bin that is determined by the red square, the green square there. The way this can, the robot needs to acquire as information to make that happen is to associate dynamics and physics with the appearance of an object, because it doesn't have any sense of what the physics and the dynamics of the objects will look like once it throws it, right? And the system doesn't necessarily have a notion of physics. It doesn't have a notion of mass. But because we're optimizing the whole thing end-to-end, it doesn't matter. We don't really need to have explicitly the mass of the object or its moment of inertia represented to the system. It's learned implicitly because that's what it takes to learn the job. Right? And again, this is a system that has essentially a perception component, a planning network, a control network. There is a bit of a conflation of things in the field where as soon as somebody says, I want to treat things end-to-end, it assumes that we just throw one big neural network at the problem and just wash our hands and say, let the network let the network decide, right? In fact, you can be very compositional and modular and still retain those properties of end-to-end differentiability and end-to-end optimization, and enable your system to react from its from data, and still retain all the nice properties of having things you can reason about, like a perception stack that's independent from a control stack. But as long as you can propagate information between them. Another interesting thing when you take this kind of machine learning, large-scale machine learning angle and apply it to robotics is that now you have robots that are sensing information up to a machine learning system, possibly in the cloud, and then sending commands back. You can inject yourself into that system and actually have a human in the loop. The human gets the sensory outputs and actually can affect and replace itself inject itself in place of the controller of the robot. The benefit of that is that a lot of the robotics tasks that are out there are very ill-defined, right? You know them as a human. Let's say, sorting objects. It's very easy to tell a person what the problem is, what the problem statement is, what the objective is. Hard coding that into a system and deriving the right rewards, deriving the right objective function for a system can be very, very challenging. If your goal is to have to robot tidy your room, the objective function of tidying your room is actually a very complex function. But humans know what tidying your room means, right? And so if you can inject human preferences into that loop, you can actually define the problem better and optimize for the things that people actually care about. So this is an example of a system that we've built that looks like this, where you have a robot that is singulating objects onto a conveyor belt. This is the view that an operator has, which is 3D rendering that people can see on a VR headset. And they can direct the robot to point the robot at the right place to pick the object. It's a very simple setup. But what's interesting is that the people can define what the problem is, and then we can train a machine learning system on that basis to actually learn from that experience and actually achieve very high degrees of success, even higher success than the original operator has in this case. And it takes some amount of training. You need to collect a lot of data. That's one of the drawbacks of data-driven approaches today, is that they're very data intensive. But with some amount of data, you're able to learn the task entirely and have the process be taken over by an automated system. what's even more interesting is that once you have this framework in place, you can start diversifying and using this in a way that applies to any sort of task, because now the people can actually give you the objectives, and you can share the representations and share the learning about what is an object, what is a good place to pick an object. And so when we actually do co-training of multiple systems, multiple tasks together, we actually are able to improve the performance on all the tasks and get very, very high degrees of success. And this is not just for picking or grasping or manipulation, right? This general paradigm of sort of data-driven robotics can be applied to a whole bunch of problems. We've worked on quadruped locomotion, for instance. We have recent work where we look at mimicking animals and their gaits and transferring that directly onto the robots. We've done some work on very dexterous manipulation, very fine-grained, very high degrees of freedom kind of problems where we learn how to play with those bounding balls. We've applied it to the problems of navigation, where this is another problem where the objective function, if it's going to go from A to B, can be well defined, but you also want to be cognizant of humans being in the way. You want to know, or dogs being in the way, and actually avoid them and act intelligently around them. And you can use this kind of data-driven approach to express what is the desirable solution that you want to explore. So this is kind of my pitch today, is that there is something interesting here about robotics and machine learning, and that brings something new to the table to the world of robotics, but has a very different shape, right? We're not used to having robots being just part of this bigger ecosystem where there is machine learning involved. There is a significant amount of infrastructure around it. It's not a common way of deploying robots in the real world today. They're mostly individual entities. It's starting to feel like the old dream of cloud robotics that Ken has been sort of pushing forward for a while is finding its killer app, right? Before, there was this need for actually having this kind of very high throughput data processing. The value proposition of cloud robotics was not entirely clear. Now with actually this data-driven approaches, it's becoming very clear that there is a lot to be gained from looking at this perspective and working with that model. That's all I had today. If you're more interested to look at the kind of research that we're doing, feel free to go to g.co/robotics. This is my team's page. Like Ken say, I also enjoy to talk about research in general and machine learning on Medium. So if you're curious, drop by, and I'm happy to entertain questions.
If you could say a little more about the use of cameras, RGB versus depth. I saw that you had one example where there is depth in there. So I'd like to just hear a little more about your thoughts on that, because I think those sensors are becoming more commodity and the quality is increasing. And then the other question is, if you could say a little more about this new application that we've been reading about at Google, which is home recycling, and why you've chosen that and how that fits into this framework.
Okay. Yeah. It's true that the RGB and depth cameras have gotten very commoditized and are getting a lot cheaper and better, and so the space is thriving on its own. The issue that I've had with using those is that in the past they were very high level of noise, and they have corner cases that are really, really damaging, like the problem of translucent materials and things like that. I also feel intuitively that they they solve a problem I don't have, in the sense that they're trying to be too precise for things that we may not need, and actually sort of reasoning more geometrically and more semantically about the world has some benefit. An example is SLAM. Right? SLAM gives you a view of the world that's point clouds, very high degree of precision, lots of data, very large data structures, but they don't give you anything about the semantics. And until you reason about the semantics, actually operating in the real world is hard. You don't know what a door is. You don't know if that blob of pixels here is a person or a fixed object, right? So in a sense, they're doing too much and not enough, right? And so I want to tilt that balance. We have experiments where we find that for things that are more 3D, where we need to reason about depth more precisely, an alternative to depth cameras is put more cameras, right? And you just put 2 or 3 of them. There are a couple of tricks. You can use what we call sensor dropout, which is to just turn off randomly one of the cameras so that they can not co-adapt and co-train. But that works actually pretty well. Whether that's the right answer down the road, and whether the industry around depth camera is going to get to the point where it's improved well enough that we should be using it everywhere. The experiment that you saw with the kitting experiment was all using depth information, right? And for that task, it's actually, as long as you're on a tabletop, fixed illumination, it's perfect. It's actually very, very useful. I can't talk too much about the other aspect that you've talked about. This is work that our colleagues at X have been doing recently and have publicized. It's called the Everyday Robot Project, and I encourage you to go and see their work. We're collaborating with them closely on the technology front. They're trying to basically bring robots into the real world in a big way, and trying to understand how can robot be put to good use in a human-centered environment. And I think it's a very exciting direction. A lot of what we're trying to do is gated on data. Right? That's the dirty little secret of data-driven approaches in robotics, is that they take a lot of data. The grasping experiment that I told you about was 4 terabytes of data. That's a lot. That's months of data collection. This is not sustainable unless we actually have robots in the real world that can actually acquire that volume of data in an inexpensive manner.
Hi, my name is Cody. I'm a master's student studying mechanical engineering here. I'm just curious if you could speak more about the throwing arm, the throwing demonstration that you showed, and why that's independent of mass, and especially like mass distribution, or how it's learning in that sense.
Yeah, the system basically learns from experience, right? So it will learn to grasp objects, and then it will try to throw them, and obviously will get it wrong in the beginning. But it will adapt to the erroneous trials and learn how to correct its torque to actually get the objects in the right place. What I was trying to express is that everything about the mass or the moment of inertia, if it is encoded in the system, is all implicit, in the sense that we never surfaced any, or we never measured explicitly what the characteristics of the objects are. And they all derive from experience throwing things, and from the perception telling us which object essentially the system is and how it should behave. You saw there were some toy bananas there. Toy bananas compared to real bananas behave very differently. If the system is not capable of making the difference, then it has no chance, right? But the system has, to some extent, generalized in the sense that it uses parameters that are plausible based on the geometry and shape of the system. And one other interesting aspect of this system is that it's actually learning online. The throws that you were seeing there, the system was actually training at the same time. It's not a batch, train once, deploy. It's actually a continuous loop that continuously refines itself and improves. So you can throw more objects into the bin. It will eventually pick them up and start throwing them and get them to go into the right bin. This kind of super adaptive systems are super exciting.
So just one comment on that one, because we use a trick of just having a scale underneath the bin. So when the object, when the robot lifts the object, it actually could get an estimate of the mass. Do you use that?
I don't believe so.
You don't? Okay, you just
it's
know
not
that.
my work, so I don't want to. But I'm pretty certain we don't.
Okay, all right. It's a beautiful result. There's another question across the room.
Yeah, yeah, I have a question. Thanks for your talk. So I'm a visiting researcher from France as well. I have questions concerning multi-agent learning in robotics, where typically decentralized one, where each robot is learning for itself. So from your point of view, what are the interesting challenges and possible solutions in maybe reward shaping also on how we can tackle this if you want to build coordination, for example, between agents or things like that?
Yeah, we haven't spent much time looking at this problem. I know that it's a very fertile academic space to be looking at multi-agent coordination. There's a lot of applications that have that shape. I don't have much intelligent to say, to be honest, because I think while it's interesting, it's not been our focus. The challenge to me is to try and find ways to hit the real world as quickly as possible, because once we are in the real world, we can collect data. And I haven't found the right shape of a problem that would involve multi-agent robots that I would be happy to just say, let's do multi-agent research in the real world. So a lot of that work seems to be happening a lot in simulation and in sort of synthetic environments.
So it's all work now. Okay, thank you. I was wondering, because here the perception is all about visual perception, and it sounds like, based on the semantics, you also had an idea of whether it was graspable or tossable. So do you think that the sense of touching also was learned by the agent? And if that's true, like, do you guys actually wonder whether like sound or actually environment learning could be used to enhance all of that?
I think it's completely underexplored, mostly because it's very easy in simulation to get visual simulation of things. It's a lot harder to get accurate tactile simulations or sound simulations. And it's also hard in the real world to have good tactile sensors that are robust enough for this line of research to be taking place. So it's very underexplored. I think there's a lot of value there there's a lot of things that we know as humans, even simple manipulations, that we have a really hard time. There's some experiments with people numbing their fingers and trying to accomplish routine tasks and being completely incapable of doing it. So there is definitely positive evidence that just the visual signal is really crippling, and we should be spending a lot more. We did mount some microphones on our robot arms, and we recorded the audio, but we have, as far as I know, not done anything with it yet. But one of the things that's difficult for visual stack perception is to understand whether there's contact or not, right? So the difference between this and that is visually minimal. But sound or any sort of other form of modality is what informs us about contact, and contact is a big deal. As soon as you want to have a robot do things, you want to understand that very well.
Yeah, thank you for sharing your work. I have a question on your bin picking work. We sort of saw two examples. One was where you were learning end-to-end with reinforcement learning way, where perception and action were coupled together. And then in the tossing bot, we kind of separated like a perception module and then kind of residual learning module, which is kind of trying to correct on top of it. Do you think it's better to take actions and kind of learn perception loop separate and action loop on top of it, or you kind of see more as an end-to-end mechanism as a better way of teaching new tasks to robots?
Yeah, the two tasks are slightly different in the sense that the tossing one has some dynamics involved, and so you cannot just do Cartesian control. In the picking task, the actual dynamics, the actual motions are very simple, right? It's go to XYZ coordinates, close gripper, open gripper. So the actual actuation stack, if you will, is not very important as a part of the thing. And so it's easy to have just one big system that goes end to end and reasons about both. In the tossing case, there is more about the dynamics involved. The other aspect of the tossing versus the picking vote is that the tossing work was not trying to generalize over unknown objects. Right? It's actually overfitting to whatever objects are in the bin at the time and learning from those. We were not trying to sort of explore more. So the setting is slightly different as a result. The task is easier in many ways. It's easier on the visual side because you can just overfit to the ping pong ball or whatever it is. It's a lot harder on the physics side because now you have to reason about the trajectory and things like this. So the balance of what mattered in those two works were different, and that's a little bit why you see that the architectures are different. I definitely don't think that we'll end up with a system that's completely just one big monolithic neural network without some sort of decomposition or some sort of factorization of the problem, mostly for data reasons, but also for interpretability reasons. In the work for the grasping work, we were trying to explore the envelope, right? In a sense, what is the simplest thing we can do? And assume that we are throwing lots of robots at it, lots of time at it, lots of scale of machine learning at it. How far can we go? And it turns out we can go pretty much all the way. That doesn't mean it's the right solution. It means that we now have an existence proof that this is actually something worthwhile pursuing, and then there is a ton of work that is happening walking back from that and trying to understand how do we make it more data efficient? How do we actually make it usable in a real sense? I could give another talk on just what happened after this and how we actually explored a lot of the deficiencies of that. Once we had this proof point that this was a viable way of approaching things.
We have time for one more question over in the corner there.
You had one.
Over there in the blue. Go ahead.
Hi, I'm Rashik, an undergraduate here at Berkeley. Thank you for coming and giving us our talk today. And I have a question regarding, like a lot of the work you guys do at Google is like very data-driven. One of the approaches that you guys have known for is not giving it very much direction in AlphaGo, AlphaZero, and as we mentioned today, with not giving it much input to how the robot needs to move. I was wondering, like, what would your approaches be if you didn't have a lot of the resources you guys do? Say, not enough data, maybe not enough time, or not enough memory, or anything of the sort, or not enough human experience.
We're somewhat deliberate about exploring this space of high data, high compute intensity because, well, honestly, we're the only ones who can do this, and somebody should, right? You need to understand where the envelope of things are. And so we're very deliberate in picking the big and dumb solutions first, because if they work, then we have a path to sort of make that more efficient down the road and not presume on the solution. To make it more efficient, there's a lot of work that's going on that tries to really understand how do we turn this kind of theoretical upper bounds into something that is actually practical. Things that I haven't mentioned here, the grasping here did not pre-train the visual models. Just pre-training a visual model helps data efficiency by some factor. You can do a lot more with simulation and pre-train with simulated data and then trying to do simulation to reality transfer. That helps a lot as well, and that makes things a lot more practical. You even get a debugging of your system for free to some extent. There is a lot of algorithmic developments that are happening that are also trying to address directly this data efficiency problem and scalability. The system that we would be using today would not have this many GPU workers and this many CPU to just marshal data around. There are ways of making that a lot more efficient with more modern techniques. I really like this kind of walking backwards and taking something that's very simple conceptually but big, and then trying to only add complexity when it actually builds brings something to the table. Going the other way is a risk of always sort of underfitting on the problem and not really sort of coming up with a complex solution to a problem that, you know, if you knew that what the solution was, would have a much simpler solution. But you know, that's also where academia shines, right? I think a lot of academic institutions are more in a constrained space, and as a result, that fosters creativity in a way that is a lot more productive.
So thank you so much. Really,
Thanks.